This is Geometry Unit 2, Lesson 6 on the multiplication and division postulates. In the previous lesson, we talked about the addition and subtraction postulates, which basically says equal quantities may be added or subtracted on both sides of an equation. Well, the process is basically the same for multiplication and division postulates. You're just going to be using multiplication and division. So let's look at the multiplication postulate first. The multiplication postulate says both sides of an equation may be multiplied by equal non-zero quantities. Now, why would you have to say equal? We know why you have to say equal, but why would you have to say non-zero? Well, what happens when you multiply both sides of an equation by 0? It's going to equal 0. So, for the multiplication postulate to work, both quantities have to multiply by the same thing, but it can't be 0, or you're not going to have anything. So, if we have a equals b, and I want to multiply by x equals y, line up your equal signs, multiply this, a times x is a times x, b times y is b times y. So if a equals b and x equals y, by the multiplication postulate, ax is equal to by. We're multiplying both sides of the equation by an equal quantity. Now, where do we use this? Sometimes you have segments and angles a lot of time in these that you can multiply dealing with doubles or triples of the size of the angle or the segment. But where we also use this a lot is when we're multiplying to get rid of getting rid of fractions in an equation. So when you see a problem like this, x squared over 6 plus 2x minus 1 over 3 is equal to 1/2, can't we get rid of the fractional denominators by multiplying by the LCD? Yeah, your LCD here is 6. If I multiply this side of the equation by 6 and this side of the equation by 6, that's going to cancel out my problem, or my denominators. So the 6 will cancel the 6 here. 6x squared over 6 is just going to be x squared. The 3 will cancel the 6, leaving a 2, so this is going to be 2 times 2x minus 1. And then on the other side, the 2 will cancel the 6, and that gives me a 3, so 1 times 3 is going to be 3. And then we can just go through and solve the equation as we normally would. So the reason that we can do this is because of the multiplication postulate. I'm multiplying this side of the equation by 6, and I'm also multiplying the opposite side by 6, so I'm not changing the value of the equation, I am just multiplying it by the same thing. The division postulate. The division postulate works basically the same thing as multiplication, except you're using division. Now the division postulate says both sides of an equation may be divided by equal non-zero quantities. Now we know about the equal part, but what about the non-zero? Why can't we divide by 0? Remember my poster out front? Can you ever divide by 0? No, you can't. That's undefined. So as long as your quantity is not equal to 0, you can divide by it. So if you have a equals b, and you want to divide it by x equals y, then you end up with a over x is equal to b over y. You're taking an equal quantity and dividing it by an equal quantity, and their quotients are equal. Now, we use this all the time when we are dealing with solving equations. 4y equals 3x plus 20. Well, if we're solving this for y, wouldn't we divide this by 4? Now, can we just divide the 3? No, we've got to divide the entire thing. Everything on this side also has to be divided by 4. So that gives me y equals 3/4 x plus 5. All right, what you divide on one side of the equation, you must divide on the other side of the equation. So we're dividing this entire quantity, 3x plus 20, by 4. I just did it separately so you can see where I got the values from. So the division postulate means that you divide each quantity on each side by the same value. Now, when you're dealing with angles and segments and that kind of thing, there is a variation of the division postulate that we actually use quite a bit. Halves, or thirds or fourths of equal quantities, are equal. So if we have a equals b, then we can automatically say half of a will equal half of b. Now that comes in handy when you're dealing with stuff that's has a midpoint or has been bisected, because you're taking half of a quantity. Now let's look how the division postulate actually applies if we're dealing with angles and segments and that kind of thing. We are given that ABC and ADC, angles ABC and ADC are congruent. So ABC, which is this angle right here, is congruent to angle ADC, ADC right here. So those two angles are congruent. Then we are given that the segment DE, this segment right here, bisects angle ADC, which is this angle right here. And also BF, this segment here bisects this angle ABC there. All right, now notice the angles 1 and 2 are marked in this diagram. What does a bisector do to an angle? Well, a bisector will divide an angle into two congruent angles. Now, don't we have angle 1 right here? What do we know about the measure of angle 1? Well, if this angle right here is bisected, if ADC is bisected, what would be the measure of angle 1? It'd be equal to half of angle ADC. So I'm going to write that down. The measure of angle 1 is equal to half the measure of angle ADC. The reason for that is because a bisector divides a segment, or divides an angle into two congruent angles. A bisector divides an angle into two congruent angles. And each congruent angle would be half of the original angle, correct? So that is the reason we can say that angle 1 is equal to half of that. All right, can we say the same thing for angle 2? Yeah, angle 2 is half angle, the measure of angle 2 is half the measure of angle ABC for the same reason. So when an angle is bisected, each piece is half of the original. So these are halves of the original segments. So what did we know about ABC and ADC originally? Well, they were congruent. So can't we say that half of the measure of ABC is equal to half the measure of ADC? Because we know that these two quantities are equal, then we can take halves of them. Halves of equal quantities are equal. All right, so we knew that ABC was equal, so we can take half of it. Now, if we look back here, I have half ABC. Do I see half ABC anywhere else? There's half ABC. There's half ABC right there. What postulate could I use to rewrite, instead of right here, what could I write right here? Well, I could write the measure of angle 2, because that's equal to half of ABC. And also, if I look at ADC, don't I see that somewhere else here? Half of ADC is right there. Okay, so instead of writing half of angle measure of angle ADC, I could say the measure of angle 1. What postulate am I using? I'm using substitution. So I can prove that angle 1 is congruent to angle 2. The measure of angle 1 is equal to the measure of angle 2 using the division postulate, halves of equal quantities are equal. Now you may be thinking, how come I can't just use subtraction? Well, think about this for a second. What do you need to subtract things? You need two equal quantities. All right, we do know that these two angles are equal, the whole angles. And we know that this angle and this angle are equal, and we know this angle and this angle are equal. But do we know if this angle here and this angle here are equal to subtract? No, we don't. We know they're equal to the one next to them, but we don't know if they're equal to each other. So that's why we're using division instead of subtraction to prove that those angles are congruent. Okay, so that is the multiplication and division postulates. Basically what you have to do is multiply or divide both sides of the equation or expression by an equal quantity in order to get a final answer. So that is the end of this lesson.